So as I said, looking at the test, problem number 9, p squared minus 7p plus 9 for p equals negative 5. This is one that actually usually has quite a few people get it wrong. This time around there was a few, but not a lot. So I was really happy with that. But the big problem that usually comes up with this question is people will put it in their calculators. Obviously it's negative 5 squared minus 7 times negative 5 plus 9. And if you enter this in your calculator and don't do it correctly, your calculator is going to take negative 5 squared and return a negative 25, which we know is not true. Negative 5 squared, or negative 5 times negative 5, is a positive 25. When you enter it in your calculator, you have to use the parentheses just like I have it written out there. Then, of course, minus 7 times a negative 5 is going to be a negative 35. So now you have 25 minus a negative 35 is the same as 25 plus a positive 35. That adds up to be 60, plus 9 is 69. Otherwise, I can't think of any others on there that were like, a lot of people had them wrong. Most of them were pretty hit and miss. Almost every question had somebody miss it, but none that were really, really popular. And as I said, if you're doing those corrections and you're not sure, just make sure you ask me, and I will, or ask a friend, talk to somebody who got it right and see how they did it. Make sure you know how to do them. Okay, with that, let's get back into new material then. I'm going to start out with just a little bit of review of the end of Unit 1. With something like this. If I'm given the command to solve. Remember, we talked about these as being, these equations have been built, they started out as a variable equals a number, and they're built from there. And when we're asked to solve, what it's asking us to do is to take it apart and get it back to that original form of the variable equals a number. So our first step is to figure out how it was built. And we did that by looking at the equal sign, right here, and identifying which side has the variable on it, which is the left side here. And we have to ask ourselves on that side of the equation, what is keeping the variable from being alone? And in this case, it's 3 and 9. The 3 is multiplied and the 9 has been subtracted. So what has been done to our variable? What's been done to x here? Well, what would happen first? Subtracting 9 or multiplying by 3? Well, careful. Order of operations is you'd multiply by 3, then you'd subtract 9. But when we go to take it apart, remember, you always take off the last piece first. So you reverse the order. So the first piece we're going to take off is the subtracting 9. And we're going to remove it by adding 9. I know you knew what you meant. You're thinking ahead of us. Yeah. So we're left with 3x. 33 plus 9 is 42. And now we have to get rid of the 3. It's multiplying our variable, so we get rid of it by dividing by 3. X equals 14. And as always, we can double check our answer by putting that number back in for our variable. So instead of 3x minus 9, it'll be 3 times 14 minus 9 equals 33. And of course, 3 times 14 is 42, minus 9 is 33. Get the same value on both sides of the equation. So I want you guys to try this one on your own quick. So what do we do first? Subtract 3. Good. So we're left with 42. That's gone. Equals 7y. And then? Divide by 7. Perfect. Divide by 7. So 6 equals y. And of course, you can put that back in for y and double check it if you wanted to. I'll leave that up to you guys. Now, of course, these became more difficult as we went through them. We ran into things like this. So looking at this, we identify our equal sign as always. We identify which side the variable is on, and this time it's on the right side. But we notice again that the variable x appears twice. Now, thinking of that balanced scale will tell us what we can do with it. Can I combine the 5x and the 2x? Yeah, yes, we can, because they're on the same side of the scale. So I can just push them together into one big pile. 5x and 2x make 7x. And we still have the plus 8. So 64 equals 7x plus 8. And now we're going to solve the equation. What's the first thing we're going to do to take that apart? Subtracting 8. Very good. So 56 equals 7x. That 8's gone. And then divide by 7. So 8 equals x. Again, you could double check that in there if you wanted to. So looking at this one, once again, we find our equal sign. But we go to identify which side the variable is on, and there's one on each side. So again, thinking about the balanced scale, can I combine the 5y and the 2y here? Yes. Well, careful. No, we can't, because they're on opposite sides. We can't just push them together. So what I have to do is get rid of one of them. Which one do I want to get rid of? 2y. The 2y, because it's smaller. Exactly. We get rid of the smaller one, usually works best. So 2y is smaller. I get rid of it. Mathematically, we get rid of something by subtracting or taking it away. Subtracting 2y, and it's gone, leaving us with 21 over there. But again, that balanced scale says we have to take 2y off the other side as well. I can't take it away from 9 because they have different names. I can only take it away from the 5y. So 5y minus 2y is 3y. And I still have the positive 9. So what do I do next? Subtract 9. 3y equals 12. And then divide by 3. Y equals 4. And again, we could go back and double check that. Let's do that just once here. So 5y becomes 5 times 4 plus 9. 2y becomes 2 times 4 plus 21. 5 times 4 is 20 plus 9 is 29. 2 times 4 is 8 plus 21 is 29. Any questions? Okay. Why don't you guys try this one on your own? Okay, so where do we start on this? Good. We have to get rid of one of the x's. We're going to get rid of the 7x, the smaller one. So it leaves us with 23 over here. On this side, what's left? 2x and the minus 11. Now what? Add 11. So 34 equals 2x, and then we divide by 2. Very good. So 17 equals x. Okay. One of the other things we did at the end of the last unit and on the test was running into things like this. where you might be told that A equals 12, M equals 9, and B equals 3. And the command you might be given is to evaluate. Evaluate means to give a value to. So on this one, we're solving for M, evaluating for M. To do that, we have to replace the variables that we have here with the values we're given over here. So M equals 7A is going to become 7 times 12 minus 4M is going to be 4 times 9. And all over 2B becomes 2 times 3. And now it's just order of operations from here. Just like in any other order of operations problem, we have the fraction bar, which is a enclosing symbol. So we have to do everything on top first. On top, what do we need to do? 7 times 12 is 84, so that's gone. Next, what do we do? 4 times 9 is 36. Now we could do a negative 4 times 9 and get a negative 36, but that would be 84 plus a negative 36. Or you can just leave it as 84 minus 36, which is the same thing. So now we're going to subtract. 84 minus 36 is 48. On bottom, what do we do? 2 times 3, which is 6. And then perfect. 48 divided by 6 is 8. So M equals 8 is our evaluation of that. So if I give you something like this, where P equals 16, X equals 9, and M equals 3, and Q equals 3. Evaluate for D. I'll give you a couple minutes. Okay, so let's put our values in here. First, this is going to become 16 times 7x will become 7 times 9 plus 2 times 3 over 8 times 3. It will be 24, but we got to wait a little while to get there. So now what? 7 times 9 is 63, and then 2 times 3 is 6, and then 63 plus 6 is 69. 16 times 69. 1,104. Good. On the bottom there, we still have the 8 times 3, which is 24. Good. What do we do from there? We divide that out. It is what? 46? Okay, 46. Cool. So now we're wondering, why are we reviewing all this? Well, because our next step, we're going to be moving into applied problems. We might start out with applied problems dealing with formulas. For example, one formula you might use is profit is equal to total sales minus total cost. Let's say we have a product that we purchase for $27 per unit and sell for $45 per unit. How many do we have to sell to earn a profit of $846? Well, we've got to do two things. First of all, we have to plug numbers into this formula. If we let X be the number sold, Our profit is the 846. Total sales is the sales cost, sales price, times the number sold. So total sales are going to be 45 times X, or 45X. Minus total cost is going to be the amount per item, cost per item, times the number sold. 27 times X. So I'm going to pause here. Any questions on where the 45X minus 27X came from? It's 40. We sold them for $45 each, times X is how many we sold. That is our total sales. We purchased them for $27 each, times X. That is our total cost. So now we can combine. The 846 isn't going to change, but we can combine what? 45 minus 27 is 18x. Good. And then divide by 18, which will give us 47 equals x. So we have 47 items sold to earn a profit of $846. Now another formula we have is the simple interest formula. I equals PRT. Over 100. So in this formula, let's say that we have, you want to earn $160 in interest on an investment of $24,000 in the period of, well, let's go 1 year. So what we have here now, when we plug this in, we've got 160 as our interest, 24,000 is our principal. Trying to find our rate. Our time is 1 year versus over 100. So, to figure this out, we're going to, I screwed this up. This isn't going to work with the darn, but oh well. Anyway, to solve this, we can combine the 24,000 and the 1, give us 24,000 times R. Then we could divide by the 100. So 240 equals R. Now we go to divide here. We're going to divide by 240, which will give us 0.666667 is R. Bad example. That should have came out to a whole number percent. But, oh well. 2/3 of a percent basically is what that's coming out to be. So anyway, we can use those formulas where we have to both evaluate the formula, plugging the numbers into the formula to replace them, and then solve the equations. Also, we're going to look at examples from geometry. And looking at geometry, we're going to look at our simplest geometric figure, which is that right there. That is just a location, or what we refer to as a point. It has 0 dimensions. All it is just a spot on the paper. But everything in geometry is created from a point. We can take that point and we can drag it or move it in a single direction. And what we've created is what we call a line segment. Now, a lot of times we just call that a line because for all practical purposes, that's the most useful form of a line. A true line goes on forever in both directions, but in practical applications, that's not really useful. So a segment is what we normally refer to when we say the word line. The length of that segment is just equal to the distance that I moved that original point. So we moved in one direction. No boy band comments there. Gives us one-dimensional. We can measure a length. We got one dimension that we can measure there. If we take that point and we keep moving in a single direction and we keep going forever, we get what's called a ray. So a ray has that starting point and it keeps going in a single direction. Now the ray's only dimension, since it goes on forever, we really can't measure its length, so its only measurable quality is its direction. Now we haven't talked about angles or anything like that yet, but the way its direction is measured is off of, like a map, you have the east direction. That would be the 0-degree direction. This all goes back to navigation. So something like this, that might be in the 20-degree direction. That is the only measurable quality of a ray, is its direction from its, if you place its starting point at the center of that grid, what its direction is from that starting direction, the 0 degrees. If I take that point that has a ray on it, and I construct a second ray, go back to that same starting point, and I create another ray going in a different direction. What we have created there is called an angle. So an angle is nothing more than two rays from the same starting point. The size of the angle, which is this right here, what's between the two rays, the technical definition is the difference in direction. So let's say, just like over here, let's say this is the 20-degree direction for this ray here from the 0 point. Let's say this ray up here is at the 70-degree direction. So the size of the angle in between here would be 70 degrees minus 20 degrees, or a 50-degree angle. Now this definition of angles was a lot more useful several years ago when the navigation skills was more common, when a lot of people looked at maps and used that angular direction. 0 degrees here, 90 degrees was due north, and so on around the map. Navigation like that is not so common anymore. So an angle has now been defined more off of benchmarks. A complete and full circle, or full turn, is 360 degrees. So then we measure angles based off of a fraction of that full turn, or 360-degree angle. So let's say I have an angle here, a ray that goes this way, and my second ray is a complete half turn in the other direction. How many degrees would that be? 180. Very good. Or if I have a ray and my second ray goes in an exact square corner, that's 90 degrees. Very good. Or 1/4 of the 360. And all other angles can be thought of as fractions of that. Again, the technical definition is this difference in direction up here. But most of us, again, aren't that familiar with navigation anymore. From these benchmarks, we have the full turn, 360. We have the opposite direction, or a half turn of 180. And then the quarter turn, or square corner, is 90 degrees. We have some special names. If an angle is smaller than 90 degrees, we call it acute. Think of it this way. Smaller, acute things are usually smaller. So smaller angles are acute. If it's bigger than 90 degrees, it is obtuse. Good. Now you may have heard the terms acute thinker or obtuse thinker. An acute thinker is someone who can focus in really narrow on a situation and see all the fine details. An obtuse thinker is someone who can step back and see the wide angle view and see the whole picture, but doesn't necessarily see the little details. So those words mean the same thing all across the board. So anyway, looking at these angles, then we can define some of the parts. that starting point that both rays started at is called the vertex. Each ray is referred to as a side of that angle. Quite often we label points with letters. So let's say I label this, the vertex, as point A. An angle, it can be named by simply naming its vertex. Angle, that little symbol there means angle. Angle A refers to that angle. But a lot of times we have other lines involved. We might have something like this. Where now if this is point D here, angle D could be any one of 4 different angles here. So to reference which one it is that I really mean, I look at other points. So let's say I have point C and point M over here. This angle right here would be referred to by naming a point, and it doesn't have to be the same point. Any point on one side of the angle, so I'm going to link point M, then the point at the vertex, which is D, and then any point from the other side. So angle MDC is this angle right here. Now let's say there's a point here, point P. I could have also have called this angle MDP. Any point on this side of the angle will do, and any point on the other side will do. Nope, you could have done PDM would have been the same thing, or CDM would have been the same thing. All that matters is that the vertex is in the middle, and that there's one point from each side. Now we have some special relationships between our angles. One of our benchmarks we used was that complete 180-degree turn, or 2 rays going in exact opposite directions. But what if it isn't just a single angle? What if we have 2 angles that when we combine them create that straight line, or create an exact opposite pointing direction? Well, these 2 angles here are what we refer to as supplementary. They're supplementary because they add up to 180 degrees. So if I happen to know that one of them is 113 degrees, how do I find the other one? Subtract it from 180. Now technically, since we're doing algebra, looking at x plus y is 180 degrees is supplementary, definition of supplementary angles. This is going to be x plus 113 equals 180. Now you're absolutely correct. We could just subtract the 113 from 180, which is what we're going to do to solve the equation, and get that x equals 67 degrees. Supplementary degrees do not necessarily have to be on the same, they don't have to share a side. Up here, what we had, this angle here and this angle here are what we refer to as adjacent. What that means is they share a side. In this case, this side right here. But 2 angles that are supplementary do not have to be adjacent. I can tell you that these 2 angles, angles A and B, are supplementary. And I can tell you that this angle here is 51 degrees. To find this angle here, well, 51 plus B has to equal 180. How do I solve it? Subtract 51. B equals 129 degrees. Well, we also looked at another special relationship, which was our quarter turn, or often called a right angle, square corner, which we said was 90 degrees. If I have 2 angles that combine to make 90 degrees, They have a special name called complementary. If I happen to know that this angle here is 23 degrees, what's this angle here have to be? Well, again, definition of complementary is x plus y adds up to 90. Perfect. So now this is going to be x plus 23 adds up to 90. To solve it, we need to subtract 23. X equals 67 degrees. Once again, these two are adjacent. They shared this side here, these two angles. But and of course I knew they were complementary because this little square in the corner, this little box in the corner tells us that's a right angle. So we know they have to add up to 90 degrees because they physically fit together to make a right angle. But again, two angles do not have to be adjacent to be complementary. If I tell you that these two angles are complementary and that this angle here is 74 degrees, how do I find this angle A? Well, A plus 74 has to equal 90 degrees. And we'll solve by subtracting 74. A equals 16 degrees. Now, these two words, complementary and supplementary. If you're anything like me, 3 minutes after I'm done talking about them, you're going to forget which one's which. An easy way to remember which one is which is complementary adds up to 90 degrees, adds up to a right angle. You receive compliments when you are right. I'll be honest, I sometimes say that in my head even today, trying to remember which one's which. So if I tell you that angles A and B are complementary, and A is 4 times the size of B. Find each angle. Well, when it comes to geometry, I find drawing pictures to be extremely helpful. So complementary means they combine to make a right angle. A is 4 times the size of B, so A is going to be bigger than B. Now when I write an equation to solve this, I want to look for one being referenced off the other, because I can only have one variable. So one of these is going to be X or Y or whatever I use for my variable. The other one's going to have to relate to that somehow. Well, A is 4 times B, which tells me if I let the size of angle B be X, A would be 4 times X, 4 times bigger. So how can I use that information to find each angle? Well, 4X plus X has to add up to 90. So now I can solve that. What am I going to do? 4X plus X is 5X. Good. Remember, think of this as being a 1X. So 4 plus 1 is 5. And then from there, we just divide by 5. X equals 18. So we're all done, right? We solved our equation? No, we have to answer the question. The question was find each angle. Well, X is 18. That represents angle B. So B is 18 degrees. We still have to find angle A, which is 4 times X. So 4 times 18, which is 72. Now we can always double check. Do those two add up to 90? Yes, they do. Well, it's easier if we're just given these relationships in a picture, like this. I want you guys in your notes to see if you can find what each of those angles measures. What's the size of each of those angles, quick? So what's our relationship between these two angles? They have to add up to 180. So 9x plus 3x equals 180. What do we do from there? Perfect. 9x and 3x make 12x equals 180. And we divide by 12. Good. X equals 15. Now that's not any of our answers yet. What do we have to do? Sure. Put x in, we put 15 in for x. 3 times 15 is 45 degrees. 9 times 15, 135 degrees. Beautiful. There's one other relationship we can have between these angles. This angle right here, let's say this angle is 56 degrees. I want to know what this angle right here has to be. Well, let's look at it. This is a straight line, which tells us that this angle and this angle have to add up to 180. So 180 minus 56 gives us 124 degrees here. But this here is also a straight line, which tells us that this angle and this angle have to add up to 180. 180 minus 124 gives us back to 56 degrees. This is actually a special relationship called vertical angles. You don't necessarily need to remember this word, but it's important to remember that angles that are positioned like this, when two lines intersect, the angles on the opposite sides will have the same measurement. So this one down here, of course, has to be 124. So if I have something like this, where I give you that this here is 4x minus 11, and this one here is 3x plus 7, and I ask you to find each of those angles, what's my relationship between these two angles? They have to be equal. So up here before I was adding two things. It was 9x plus 3x equals 180. Down here I'm not combining two things. I'm making them equal to each other. 4x minus 11 has to equal 3x plus 7. What do I do now? Subtract 3x. So 4x minus 3x is 1x, or just x, minus 11 equals 7. And then add 11. So x equals 18. Now, of course, we're nowhere near done yet. We have to find our angles. 4x minus 11 is going to become 4 times 18 minus 11. 4 times 18 is 72. Minus 11 is 61 degrees. Now, a great way to double check is to come over here and do the other side and make sure we come up with the same number. So 3 times 18, x is 18, remember, plus 7. 3 times 18 is 54, plus 7 is 61 degrees. We get the same amount on each angle. Any questions? Okay, that's a good time to take our break. It is now 4:17. Let's come back at 4:27 to start our second.